a solid lies between the cone, z equals 4 times the square root of x squared plus y squared, and the paraboloid, z equals 30 minus 2x squared minus 2y squared, and it has a density at each point that is 3 times the distance to the z-axis. Find the mass of the solid. So to find the mass of a solid in 3 dimensions, we do a triple integral over the region that the solid occupies of the density with respect to the volume element. So that's the generic formula for mass. And in our case, we have a cone, z equals 4r is how I'm going to think of it. Sorry, I should have started with polar coordinates. X squared plus y squared is equal to r squared, because x is equal to r cosine theta and y is equal to r sine theta. So this is 4r. The square root of x squared plus y squared is r. So we have z equals 4r. That's a cone. I think we might just want to consider the top part of the cone with r positive. So z equals 4r. And then we have a paraboloid that opens downward, and that's z equals 30 minus, this is 2r squared. Factor out the 2, the negative 2, and we have x squared plus y squared. And so that's like it's kind of like this. And so we have an object here that looks a little bit like a snow cone. And we want to find the mass of the solid. We're going to use cylindrical coordinates. So we'll have double integral. The density is 3 times the distance. Here's the z-axis. Here's a point. 3 times the distance between a point and the z-axis. Well, that's just r. So the density function is 3r. And then we'll have r. And we're going to integrate z first because we have boundaries on z that depend on r. So we're going to integrate z and then r and theta. So what are the boundaries in the region? Z for any particular point in this, for any fixed r and theta, the z will go from the cone up to the paraboloid. So z is going to be bigger than or equal to 4r and less than or equal to 30 minus 2r squared. So z goes from 4r to 30 minus 2r squared. Theta is going to go from 0 to 2 pi all the way around a circle. And then if we look down on this object, it will just be this circle here. So theta from 0 to 2 pi, and r will go from 0 to whatever that distance is there from the z-axis. And to find that, we will set these two equal to each other. 30 minus 2r squared is equal to 4r. See where they intersect, and that'll give us the radius, the maximum possible radius in this figure. So 2r squared plus 4r minus 30 is equal to 0. Divide by 2, r squared plus 2r minus 15 is 0. R plus 5 times r minus 3 is 0. R is negative 5. We'll not use that one. And r is 3. There we are. R is 3. So r will simply go from 0 to 3. Now there's no theta in the integrand or in any of the boundaries, so all of this is a constant. The first two integrals are a constant with respect to theta, and so we can just pull them out of the d theta integral, and the integral from 0 to 2 pi d theta is 2 pi. So we'll have 2 pi times the double integral, 0 to 3, 4r to 30 minus 2r squared of the function 3r squared dz dr. So the inner integral is constant with respect to z. So we'll just plug in the so the antiderivative is 3r squared z, and then we have to plug in the endpoints, 30 minus 2r squared and 4r, and then integrate with respect to r. And this will give us, plug in this minus this, we'll have 3r squared times 30 minus 2r squared minus 4r dr. So now we have a basic integral of, it looks like it'll be a fourth degree polynomial in r. A fourth degree polynomial, and plugging, when we integrate, we're going to get a fifth degree, and plugging in 3, we're going to get some perhaps unwieldy numbers. So let's distribute to 3r squared, and we'll put the powers in, let's say, increasing order. We have 90r squared, and then we'll have minus 12r cubed, and then we'll have minus 6r to the fourth. So antiderivative is r cubed over 3, 90 over 3 is 30, r to the fourth over 4, 12 over 4 is 3, and here nothing cancels, we're left with the heinous fraction 6r to the fifth over 5 to make our arithmetic even more fun. And we have to plug in 3 and 0. When we plug in 0, we will get 0. So we'll get our answer when we plug in 3. 30 times 27 minus 3 times 3 to the fourth is 81. There we are. I accidentally wrote 3 to the fourth. And then minus 6 times 3 to the fifth over 5. And I did the arithmetic earlier, so I know that the final answer, this number times 2, is well, after you convert to fifths. So I'll leave this for you as a calculator exercise. We'll get 2754. That was easy to remember. 27 times 2 is 54. And then pi all over 5. So that's a little bit of a mystery step there, but it's just arithmetic. So I'm not going to worry about that. I used a calculator, so can you. 2754 pi over 5. We found the mass of a solid by integrating the density over the volume of the space that the object occupies. And it was a round object that worked very nicely in cylindrical coordinates. We notice that there's x squared plus y squared in the formulas for the objects, and x squared plus y squared in cylindrical coordinates is r squared. So that was another giveaway to use cylindrical coordinates.